Okay, good afternoon, everybody. So, new topic, point estimation, and we'll start with concepts and properties. So basically, the concept of point estimation is when you have a population, you usually don't know information. You don't know the parameters of the population. Okay, in this case, let's say mu and sigma squared for a normal case. And what you do, you take a random sample, by the way, IID sample, which is what? Independently, identically distributed. That's the definition of random sample. And then you define a function on that to estimate basically mu and sigma squared. And we call this point estimation. Okay? Today, I don't teach how to do the point estimation, but I tell you if you have a point estimator, if you have a function, how you can evaluate that point estimator or function. Okay, what are the properties that we care, and we say if basically what are the criteria for a good estimator? Okay, then hopefully next week we'll start talking about different methods for point estimation. And as I said, this lecture and a couple of lectures after that, it's going to be just mathematical. And then hopefully after we finish point estimation and we start basically interval estimation and hypothesis testing, that would be more applied, much easier. Go ahead.
Was the random point estimation you showed with the software a viable approach, or was that just to show that when a distribution is randomly sampled, it tends toward a normal distribution?
Oh, yeah. Actually, these are the things that we are going to talk about. Exactly. So we want to talk about if you have estimator, what would be the average of that estimator? What would be the variance of that estimator? And how we can decrease that variance. Okay? Yeah. But before that, let me just review what we had before, sampling distributions. If we have only one population and we want to know what is the distribution of X bar, you remember? And we know the variance. What is this distribution? Normal distribution. If we don't know variance, it would be T distribution with n-1 degrees of freedom. So that's the distribution of X bar. Okay? What is the distribution of basically sample variance when we have one population? We model it by chi-square with n-1 degrees of freedom. How about two populations? We have two populations, variances are unknown, and we want to know what is the distribution of difference of X bars, or difference of basically sample averages. Normal, and if we want to know the same thing like the difference, the distribution of difference of X bars or sample averages, when we don't know the variance, it would be T with n1 plus n2 minus 2 degrees of freedom. What is the main assumption here? Remember? Variances are equal. They are unknown, but they are equal. And finally, the ratio of the variances, sample variances, following F distribution with n1 minus 1 and n2 minus 1 degrees of freedom. Okay? That's basically a summary of all sampling distributions. Okay? So let's just start with the estimator. Let's say we have a population, and this population could be, let's say, the height of people, or the length of manufactured part, or could be the waiting time in a queue. Okay? So we have a population and follows a distribution with this form. It's a very general distribution. And there is one or more than one parameter that we don't know. Okay? So in this case, theta is the parameter of distribution. So what we do, we collect a random sample or IID sample, and we define a function. And using this function, we want to estimate this parameter. So usually what we do, we show the estimator with hat. So theta hat is estimator for theta. This is called point estimator. Why we call it point estimator? Because it gives you just one number from one parameter. It's point estimator as opposed to interval estimator that you will learn later. Go ahead.
But do we have to already suspect what the distribution is?
Yes. That's a very good question. We should know what the distribution is, but we don't know the parameter of the distributions. But the question is, in reality, how do we know that? So later on, I think towards the middle of the semester, you will see some hypothesis testing that you can use to test the distribution of basically a random variable or a random sample or basically a population. So what you do, you plot histogram first, and based on histogram, you say, okay, maybe it's close to normal or it's close to F distribution, and then test if it's coming from a normal distribution or a gamma distribution or exponential distribution. Okay? But for now, we assume that we know that. Any other questions? Okay. Yeah, the PDF is basically, so let's say for exponential distribution, it's this. So that's the PDF. Lambda e to the power of lambda x. So it depends on lambda and x. X is your random variable, okay? And lambda is your parameter. So this should be known, okay? If it is not known, we use that random sample to estimate it, okay? So we call that function, this function h, as point estimator, okay? As soon as we collect a sample, then we can get numbers. Let's say we have a sample of 10 parts. We basically measure the length of them, basically these 10 parts. I have 10 numbers. I fit into that function. What happens? I get a number. Okay? That number is called point estimate. So the function itself is called point estimator. The number that you get is called point estimate. Okay? That's just the terminology. So parameter is mu. For example, this x bar is estimator. When you get a sample, you calculate the number is called estimate. That's it. Is it clear? Any questions? So now this is very important. That point estimator or theta hat is a random variable. Why? Because it's a function of, if you see here, it's a function of a bunch of random variables. So a function of bunch of random variables itself is a random variable. Okay? Therefore, it has some distributions. And some of those distributions you've seen before. For example, you know x bar has distribution. S squared has some distributions. And that's basically what we are going to use to evaluate the performance of those estimators. Let me give you some examples of point estimators. For normal population, what is the estimate for mu? X bar. What is estimate for sigma squared? S squared, which is the sample variance. What is the, for Bernoulli distribution or binomial population, where you have either 0 or 1. It's working or not working. It's good or bad. It's positive or negative. Then the best estimator is the number of, you collect a sample, okay? And this random sample is either 0 or 1, okay? You count the number of success or non-conforming point divided by basically the sample size. So in this case, your p hat would be what? 3 over 5. For the subtract, for the difference of mu is the difference of x bars. Difference of p's is the difference of p hats. So these are like some examples of point estimators. Any questions?
Variable that's inherent to the distribution, though, like lambda, like a coefficient.
Yes, it could be any distribution. It could be any parameter of that distribution. Okay, so you can see different distributions here. This is Bernoulli. This could be from normal. This could be from exponential. Anything. Okay, so let's start with basically properties and criteria using which we evaluate a point estimator. Okay. So the first criterion is biasness, or basically we called a point estimator like theta hat as unbiased estimator if this condition meets. If this condition basically holds. So let me tell you what bias means. So you have your random sample. These are a bunch of numbers. You calculate X bar, it gives you one number. Okay? So let's say it gives you 5. Okay? And let's say your true mu is 4. Okay? Then you have another sample. Bunch of numbers. It gives you another X bar. Let's say this is 4.5. Okay? You have another one. Let's say it is let's say this is 3.5. This is 4.5. And so on and so forth. So you can see every time that you collect a sample, your X bar could be a different number. And the reason is because X bar is a random variable. Every time you collect a sample, you could see different, basically, observations with different values. Does it make sense? Every time that you collect sample, you get different values. And you can see X bar could be greater than mu or less than mu. So basically, it has a distribution. So if on average, or the average of this distribution is the same as your parameter, then you have unbiased estimator. I think I have a very intuitive figure here. So let's say this is the parameter, and these points are point estimator that you observe, point estimate that you observe. So you can see the average of those shots are on target. Okay? So in this case, you can say you have unbiased estimator. Okay? Which means on average, what you get from the point estimator is the same as the parameter of the distribution. Does it make sense? On average, what you get from the point estimator is the same as the parameter of the distribution. Okay? Which basically, as you see, the expected value of theta hat is theta.
Value of that parameter to confirm it's unbiased, or if it just tends.
You will see. That's a good point. You will see in a minute. You don't need to know the numerical value of that, but basically you will see in some examples that we can say, for example, expected value of X bar, which is the average, is the same as mu. So it doesn't matter what mu is. Okay, it's always true. Okay, so these are just some general properties. One other example, you can see, this is definitely not an unbiased estimator. You see that? And this difference, which is the average of your estimate from the true parameter, is called bias. Does it make sense? So this guy is called bias. The expected value of your estimator minus true parameter. Go ahead.
I mean, so if you have a bias in your estimator, does that mean that your sample is not a random sample?
No, it could be a random sample, but the estimator that you define is not a good estimator. Okay? For example, instead of X bar, you are, I don't know, using this estimator. This estimator is biased. So the function that you define is not a good function. Question? Yeah, you can go ahead.
You don't know where the bullseye is, the true parameter.
I'm sorry?
If you don't know where the bullseye is or the actual parameter, how would you detect the bias? Because you said usually you don't know the population.
Yes. So we don't know the numerical value of that population. But we know, for example, the expected value of a normal random variable is mu. Okay? And we want to see if X bar can basically correctly estimate that mu on average. Okay? And we show that, for example, the expected value of X bar is mu. Okay? It doesn't matter what mu is. It's always true. So you don't need to know the numerical value of that mu. but you can show the property.
It is doing really bad. Would you say really it's biased?
No, I would say the random sample that you get that time is outlier.
Right. But then, according to our definition, it would affect the...
Yeah, it's true. But put it this way, if you have 1 point here, then it would affect your average. Okay? Do you know what I'm saying? So if you remove that outlier, still you don't have bias. So, and what we do in reality, so we come up with some basically estimators, and we know that the property of this estimator, without observing any sample, any numerical sample, based on the mathematics, we know that this estimator should be unbiased. But if you are getting a number way different from others, you know that this is not because the estimator is bad. It's because the sample that you got is an outlier sample. Does it make sense? Any other questions? Okay. So let me give you a couple of examples. Now you see what I mean by unbiased estimator and not knowing basically the parameter of the distribution. So let's see. We have a random variable, it's population, x. The expected value of this random variable is mu, and the variance is sigma squared. We collect a random sample. We calculate x bar. We define s squared. And we claim that x bar is an unbiased estimator for mu, and s squared is an unbiased estimator for variance. We want to show that. So we talked about this before. I told you x bar is a good estimator. And now I want to tell you what do I mean by good. Okay? So if I want to show that x bar is unbiased, I need to show that the expected value of x bar is the same as parameter. You agree? That's the definition. Okay? And back to your question, I'm not assuming any number for that. It's general. I'm just showing in general whatever your x bar is or whatever your mu is, that's true. Okay? So what is the expected value of x bar? And actually we showed this before, but just to review. So it's 1 over expected value of this guy. Because this is constant, we can take it out of expected value. And expected value of summation is what? Summation of expected values. This is n mu. So n mu divided by n is mu. It's unbiased. Make sense? Any questions? So what does it mean in practice? It means when you have a point estimate, if you have an actual sample with numbers, it doesn't mean that that number is exactly mu. So what I mean by that, if you have actual numbers, let's say 2, 3, 5, 1, the average would be, what is the average? 11 divided by 4. 2.25. It doesn't mean this x bar is the same as mu. It says if you repeat this process, the average of these x bars eventually going to be mu. Okay? Or if your sample size increases, your x bar tends to go to actual mu. Go ahead. So that's actually a good question. We know X bar, expected value of X bar is what? We just showed you, is mu. Okay? So this tells you that on average, X bar is performing well. Okay? It's going to be the average of those X bars. If this is the distribution of X bar, if this is the distribution of those values, then the average of X bars and mu going to be the same. Okay? That's what it's saying. But the question is, I give you one distribution like this. I can give you one distribution like this. Which one is better? Both of them are estimators. Both of them are X bar. Okay? Which one is better? Exactly, this one, because it has a less variability. It's more precise. Both of them are accurate, but this one is more precise. And this one has larger sample size. You will see later. So larger sample size means the variance is smaller. Is it? Okay, sorry. Okay, thank you. Yeah, thanks. Okay. So let me give you a couple of minutes to show that S squared is also an unbiased estimator for sigma squared. Question? Tell me.
I guess my question is, how do you know your data doesn't really look more spread out?
Oh, I'm saying if your sample size for this case, let's say this case is 5, this case is 10. So the larger sample size that you have, the variance would be a smaller. Because the variance of X bar is sigma squared divided by n. When you increase the sample, then that one decreases. Okay, so let's see. Let's see if we can show that the expected value of S squared is sigma squared. And so basically, the expected value of that summation, we want to show this. Remember this one. You remember that? I think you need to remember something else. So variance of a random variable. Do you know the definition of this? Do you remember, anybody? It has something to do with the expected value. What is it? That's the definition of the variance. Okay. So let's see. So this expected value, this guy is a constant. I can take it out. So I need to find the expected value of this summation. Based on, let's call this number 1, this number 2. Based on number 1, we have this expected value, which is right here, is the same as this quantity is the same as difference of these two quantities. Is it x bar minus mu? Is it clear? Any questions so far? So what I did, I just used this basically equation and replace this guy in the middle with the difference of this guy and this guy. Is it correct? Any question? Always double check my calculations. Okay, so let's see. One more step. Expected value of a linear combination is the linear combination of that expected value. So I can write this down as summation of expected value of xi minus mu squared minus n expected value of x bar minus mu squared. Okay? Does it make sense? So that expected value is the summation of these expected values. And then for this guy, n is constant, so it's going to be n times the expected value of this guy. Is it clear? Any questions? Yeah. Yeah, sure.
First one, when you were showing the mean.
Oh, this one?
Yeah.
Yeah.
The first one, you say 1 over n e, and then the next step, it's substituted as n times mu over e times 1 plus
You mean here or here?
Going from that step to the next. Yeah.
Oh, yeah. So because the expected value of x1 is mu. Expected value of x2 is mu. Expected value of xn is mu. So mu plus mu n times, it's n times mu. Okay? So you're right. I think I jumped. I should have wrote it down like this. So expected value of x1 is mu. Expected value of everything is mu. And this one is also mu. How many of those do I have? N. So it's n mu divided by. Oh, no. Yeah. So let me put it this way. That's better. And then it's going to be mu. Okay? Yeah.
Last time, just to remember, you told me that the sample itself is a single variable, not a set of a lot of samples.
That's basically, x1 is a random variable. Okay? In reality, okay, put it this way. So it's the difference between random variable and realization. Okay? So before you observe the value, you don't know the value. Okay? So for you is before observing the actual value is a random variable. It could be any number. So you collect a part. You haven't basically measured the length. So that x1, which is for this part, could be any number. So it's random variable. But as soon as you measure that, then it becomes a realization of that random variable. Can you see the difference? It's a little bit tricky, but that's the difference between random variable and one observed basically value or realization from distribution. Okay. Back to this. Is it clear? From here to here? Okay. So what will be the next step? I just continue here. So I'm going to use second fact. So based on the second fact, I can write this guy as what? Variance. So it's variance of x or xi. It doesn't really matter because they are having same variance. Okay? That's the definition here. How about this guy? What is this? Is the variance of what? Is variance of x bar. Okay? So basically 1 over n minus 1 summation of r from 1 to n, variance of x or xi. I can either put the index here or not, minus n, variance of x bar. So what is variance of xi? Anybody knows? It is sigma squared. Remember, xi's are IID, which means they are identically distributed. So all of them have the same variance, which is sigma squared. Okay? So this guy is sigma squared. How about this guy? This guy is sigma squared divided by n. You remember variance of x bar? Sigma squared divided by n. So I can write this down as summation of one constant. It's n times sigma squared and minus n sigma squared n. I can cancel out these two. I factorize sigma squared, and I get this guy. Finally, I can show that this is basically unbiased estimator of variance. Does it make sense?
Qualitatively?
Basically what it says the deviation of individual values from mean, population mean. Okay? So if you have a random sample, the deviation of those random samples, those observations from mean squared, okay? So we call it variation around population mean, can be decomposed into two parts. Okay? One is the deviation from sample average, and the other one is the deviation of that average from mean. So if I want to show you, I don't know if I have, can I have a different marker color, like blue or something? Thanks a lot. Oops. Thank you. Actually, this concept, we are going to use this concept later for analysis of variance. That's a very good question. What this equation means. So let's say this is the population mean. Okay? So I'm trying to explain what this equation means. So let's say I have a sample of seven variables, let's say. So this is mu. I call this guy, so the average of this, let's say this is the average. This is x bar. Okay? So this is average of these numbers. So what it says the deviation of each individual observations from mu is the same as deviation of these observations from x bar plus deviation of x bar from mu. I mean, it makes sense. Okay? So the variation of observations around the population mean is the same as variation around the sample mean, and the variation of basically the sample average from the population mean. That guy is here. That's basically the concept. And you can easily show that, I mean, mathematically. Any other questions?
As it gets larger.
It's always true. It doesn't matter. It doesn't depend on n. It's always true for any n.
That, since n is kind of a scaling factor.
That's actually a good question. This is the variance. Yeah, I would say yes. So this guy gonna increase, this guy gonna increase, this guy gonna increase with the same, about the same rate. Go ahead.
Your sample size, the x bars will be much, much closer to mu. So the n increases, but the x bar minus mu decreases. So as you increase, as it goes to infinity, x bar equals mu. Right?
X bar minus mu will decrease just by definition.
I'm looking at the expected value. Let's put an expected value here. Okay? So if you put expected value here, this is going to be variance. So it's going to be n sigma squared. Okay? So expected value is the sigma squared. How many of them do I have? N of them. So it's n sigma squared. So when n increases, n sigma squared increases. The same thing happens here and here. Okay? So basically, both sides of inequality increases on average. On average, when you take the expected value. That's the way I look at it. Okay? Okay. So I think I need to hurry up. One more example. Actually, this example is, I think there's a problem here. This should be n, not n minus 1. Just fix that one. Let me just fix it right here. So it says, suppose the mean show the following estimator is bias estimator of the variance. I'm sorry. That's mu. That was correct. Screwed up. Yep. Okay. You remember I told you if you don't know mu, so your SS squared would be this guy. And if you know mu, this would be a better, we're good here? A better estimator. Okay? So this is a better estimator. I will show you why this one is not good, why this one is biased, and then we will see how we can make it an unbiased estimator. So see the difference between this guy and this guy. Here, we don't know the value of mu. Here, we know the value of mu. Okay? Any questions? Yep.
About last time you used sigma squared over n for the variance of x bar.
Yes. I'm using it
Then
here.
you used n minus 1.
For this guy, this is not variance of x bar. This is just the definition of SS squared. So variance of x bar is always sigma squared divided by n. Yeah. This is not the variance of x bar. This is the equation for SS squared. When you don't know mu, this is, when you know mu, I want to show you this is not a good estimator. Has nothing to do with the variance of x bar. Okay? So now, let's see. I want to show or calculate the expected value of this estimator, okay, which is the 1n minus 1, because this is the constant expected value of this guy, okay. Let me write one more intermediate step. Expected value of 1 over n minus 1, summation of I from 1 to n, xi minus mu squared. Then this would be 1 over n minus 1, summation of I from 1 to n, expected value of xi minus mu squared. Okay? So based on number 2, so what is this guy? This guy is variance. So this would be variance of xi. So this guy is variance of xi. And variance of xi is what? Sigma squared. So how many of them do I have? N. So it's n sigma squared divided by n minus 1. Okay? So this is the expected value of your estimator. Which is not the same as this guy. Okay? Therefore, it's a biased estimator. Does it make sense? Any questions? How the second part is how I can make it an unbiased estimator. Just replace n minus 1 with n. That's it. So if you change this n minus 1, make it n, then this become unbiased estimator. Any questions? Okay. So now let's say we have two unbiased estimator. So both of them are good because both of them are unbiased. Okay? And here, which one would be a better estimator? Theta 1, theta hat 1, or theta hat 2? Definitely theta hat 1 because it has less variance. Okay? It's more precise. Both of them are accurate, but this one is more precise. So what we need to do, we need to find the variance of estimate. So that's the second criterion. The first criterion was what? Bias. The second one is variance. So a good estimator is unbiased estimator with a smaller variance. Okay? So for example, one estimator for mu in a normal population is x bar. Another estimator, which is again unbiased, is x basically tilde, which is median. Okay? But variance of x bar is less than variance of x tilde, which means x bar is a better estimator. And that's why always you see that you are using x bar for estimating the mean, not x tilde. Of course, x tilde is good when we have, anybody remembers? Outliers. Okay. So that's basically the concept. So both of them on average, both of these estimators here on average are are on target, so the bias is 0, but this one is more spread, this one is more focused or concentrated, which is a good estimator in that case. By the way, so that's the variance. If you take a square root, it becomes standard deviation. Sometimes we call it a standard error of estimator. Okay, so a standard deviation of estimator, also known as basically a standard error. So one example, we know that X bar is an unbiased estimator for mu, and we know that its variance of X bar is sigma squared divided by n. So the standard deviation, also known as a standard error of X bar, is sigma divided by a square root of n. Okay? And if I don't know the value of sigma, I can estimate it with what? S. Okay? Which we call it estimated standard error. Those are just terminologies. So one example, we have a sample of 10 observations. Okay? From these 10 observations, X bar is 41.924. We can find the standard deviation, S, is 0.284. Therefore, my estimated standard error is S divided by square root of n is 0.0898. So what does it mean? It means this is the estimate for mu. Okay? But basically this guy is the deviation from this X bar, or from the basically from the mean of X bar, or from actual mu. So I can use this guy somehow to model the error of my estimation. So error of my estimation, which is difference between X bar and mu, okay, that's the error of estimation, is related to this guy. And later in confidence interval, you see how they are related. Okay? So basically your error of estimation, which is the absolute value of X bar minus mu, is related to that standard deviation. Okay? Any questions? Okay. That's another mathematical concept. It's called minimum variance estimator. So if you have a parameter to estimate, let's say mu, I can give you a family of different estimators. For example, one could be X bar, the other one could be X tilde, the other one could be X hat, which is mode, and some other stuff. Okay? And I can give you many unbiased estimator. Okay? We can show that one of those has the minimum variance. Okay? And if you want to show that, for example, X bar or some specific estimator like theta hat has the minimum variance, you need to basically show these two parts. The first one, it should be unbiased. The second part, the variance of your estimator should be equal to this bound, which is called Cramer-Rao bound. Okay? And in this case, your f of x is the PDF, this is the expected value, and this is the sample size. And this notation is derivative with respect to your parameter. I don't think we have time today, but on Monday I'll show you X bar has these two properties. Not only is unbiased, but also has the minimum variance. Okay? And as I said before, so this lecture and the next lecture again is going to be a little bit mathematical, and then after that hopefully we go to some applied stuff.